Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, so today we are going to discuss on the last subtopic for chapter 4. Chapter 4 tells about energy analysis of closed system. For this particular chapter, there is one specific subtopic that is allocated for us to discuss on ideal gas, right? So this 4.4 subtopic, specific heats, is the sections where we specifically discussed on ideal gas. Okay, specific heat is the specific heat of any materials, or specifically on gas, is actually telling you how strong or how capable of that particular gas or material to store heat. Okay, for example, we have like we require as much as 4.5 kilojoule of energy to raise a gas, a 1 kilogram of gas, to raise the temperature of 1 degree. So therefore, the specific heat for that gas is 4.5 kilojoule per kilogram Kelvin. Right, so there are two types. Okay, there are two types of heat capacity. Specific heat, sorry. There are two types of specific heat. Since the specific heat is defined as the energy required to raise the temperature for 1 kilogram as much as 1 degree, so in general, this amount the energy that required to increase the temperature is somehow depends on the process, how the process of the increment of energy is executed. So for this particular thermodynamic system, we always actually interested in two kind of system. The first one is where the system is constant volume, right? Constant volume. And then the second one, if the system is constant pressure. Therefore, the specific heat also has these two types. Depending on these two type of system. That is, there are specific heat for constant volume process, where we define as CV. It is defined as the energy required to raise the temperature of 1 kilogram of substance by 1 degree, where the volume is maintained constant. The second specific heat is for constant pressure process. It is defined as how much energy is required to increase the temperature of 1 kilogram that substance by 1 degree for the system there where the pressure is maintained. So we have these two types of specific heat. So it so depends on the how the process is executed. Alright. So basically, so this is how this specific heat is defined. So this tells you how much energy is required to raise the temperature of that particular substances, where the substance is 1 kilogram and the increment in temperature is 1 degree Celsius or 1 Kelvin. For your information, there are always difference in the amount of heat required to increase the temperature for the substance if the substance in different system. If the substance in a in a rigid system where the volume is kept constant, okay, the specific heat is somewhat lower than the specific heat or the energy, the amount of energy required to increase the same substance with the same mass and the same temperature difference but in different system, where now the volume is no longer constant, the volume is changing to maintain the pressure. All right, so if you can see here, the CV, the amount of CV is always lower, or I can say the amount of CP is the specific heat for the constant pressure system, is always larger than the amount of CV. Okay, given for the same substance, the same mass, and the same temperature difference, right? So for the same substance, the same mass, and the same temperature difference, the amount of energy required to raise one temperature, or to raise 1 Kelvin or 1 degree Celsius for constant pressure system is always larger. Why? Because for the constant pressure process, to maintain the pressure, if we refer back to the chapter 3, or the chapter where we discuss on the pure substance, there are always amount of boundary word related to the system of constant pressure. The system need to regulate the pressure in a way that it will increase the volume. So in the process of increasing the volume, there are some boundary work, okay? So there are some boundary work interaction in the system. So, and that's the reasons why more energy is required to increase 1 kilogram of the substance for 1 degree Celsius. Okay. So these two equations in figure are valid for any substance that are undergoing any process. Okay, the heating process or cooling process and so on. All right. So CV, specific heat for constant volume, and specific heat for constant pressure are actually properties, whereby CV is somehow related to the changes of internal energy. Okay, and the constant specific heat for constant pressure is somehow related to enthalpy. Okay, why enthalpy? Okay, because when we are dealing with constant pressure process, remember we have the boundary word. Okay, from the definitions of enthalpy. Okay, actually I have mentioned this in the lecture yesterday. Enthalpy is defined as I mentioned in the class yesterday. Enthalpy is actually related to total heat content of the system, which account for internal energy and energy required to increase the volume. So enthalpy is somehow defined as internal energy and some boundary work, okay, or the energy that is related to the increment or decrement of volume, right? So since CP is actually CP is somehow related to constant pressure process, specific heat for the constant pressure process, and to maintain the pressure of the process requires some boundary work. Therefore, CP, specific heat capacity for constant pressure related to enthalpy, right? Okay, so if we do the balance, okay, if we do some balance of energy balance, okay. So any heat interactions and work interactions of any system, either it is pure substance or gas, somehow related to the changes of internal energy. So this is from first law of thermodynamics, right? For constant volume, Okay, since constant volume process, there is no interaction of work, boundary work. So boundary work is somehow zero. So therefore, what is left with us is the relation between how much energy, how much heat content will change the internal energy of the gas. Alright, and as we all know that the content of energy is calculated from mCV delta T, and this is m delta U, right? So this will give, for constant volume process, it will give the relation between Cp and internal energy and the temperatures. Okay, this will give Cv, constant volume, or specific heat constant volume, is the change of internal energy and per the change of temperature. Right. Okay. Now let's look at the for constant pressure. Constant pressure, any heat interaction and work interaction will contribute to the change of energy of the system, and for the stationary system, the change of energy will contribute to the internal energy. Alright, so since we have the work boundary, okay, for example, work boundary, because constant pressure requires some work boundary, so this term, the work term, is not zero this time. Okay, we do have values. Okay, if you write the energy content in terms of mCV delta T, CV, now Cp delta T, okay, and some boundary work, it give you the change of internal energy, right? And from here, okay, we can write this equation as delta U and PV. PV is the boundary work. Okay, and if you remember, the definition of enthalpy is U and PV, right? So this is P delta V, the boundary work, right? So it gives us mCp delta T equals to delta H, alright? And this is actually mass and delta specific enthalpy, alright? So it gives us the relation between specific heat capacity and delta H over delta temperature. Alright, so this is the relation between Cp and enthalpy. Okay, and just now Cv with the only internal energy. Okay, Cv is delta U over dt, while Cp equals to delta H over dt. So we have two relations here. The first one is Cv and internal energy, while Cp is enthalpy. Right. All right. So this is where comes this relation, where this Cv is the change in internal energy with the temperature at constant volume, and Cp is the change in enthalpy with the temperature at constant pressure. So this is all the properties. Okay, so this is what we call properties relation. Okay, meaning to say Cv and Cp are actually properties because it is somehow related to enthalpy and temperature for Cp, and internal energy for temperature for Cv. So these two value is actually properties too. Right? So this Cv and Cp are properties for ideal gas. Okay, Cv for constant volume process, Cp is constant pressure process. And if actually these two value somehow, if you can see here, there is temperature factors there. Okay, meaning to say the value of Cv or the value of Cp somehow changes with temperature range, right? If we want to increase from 300, it says here, if you want to increase from 300 to 301, okay, only require 0.71 kilojoule for air. But if the temperature range now change from 1000 to increase 1 Kelvin to 1001 Kelvin, require more energy. So meaning to say, the specific heat of a substance somewhat change with the temperature range. Okay, the higher the temperature range, the more the energy required to increase 1 degree. Okay. So if you are dealing with the process at lower temperature, you only require a small amount of heat to change its enthalpy or its internal energy. All right. So here is the relation between internal energy, enthalpy, and specific heat for ideal gas. Remember, this is specific topic for ideal gas. You can only use this equation and relation for ideal gas, not pure substances. Okay. Now, this is the one that I mentioned just now, enthalpy. Okay, enthalpy is defined as internal energy and boundary work. And if you still remember equations of ideal gas, we have PV equals to RT, where the R in this case is specific gas constant. Okay. All right. If we combine these two, okay, if we combine these two questions, okay, it will give us one relation between enthalpy, internal energy, and this is, what is that? This is the boundary work. Actually, so this come from PV. Okay, P and V. Okay, PV equals to RT, right? Right, so PV here is replaced by RT. So this will give us a relation between, enthalpy, internal energy, enthalpy and internal energy of any gases. Okay, given one condition, the gas is ideal gas. Right. Okay, so meaning to say that from this relation, we can see that internal energy is a factor of temperature. Same goes to enthalpy, is also the factor of temperature. Right. Therefore, C specific heat capacity for constant volume also change the factor of temperature, and specific heat capacity for constant pressure system also the factor of temperature. Meaning to say, these values are somewhat depending on the temperature range. Okay. Right. What else? Alright, so for ideal gases, it says here for ideal gases, internal energy, enthalpy, specific volume for constant pressure and volume vary with temperature only. Okay, somehow it's depending on the temperature. Okay, and then it gives us, this is the equation how we want to calculate the internal energy change using the specific heat capacity, and also calculate the enthalpy change using specific heat capacity. Remember, you need to pay attention to this difference. Okay, difference. For internal energy, you use CV, and for enthalpy, you use CP. Alright. So this is this relation. Okay, these two relations somehow true for ideal gas at low pressure. So it says here, at low pressure, all real gases approach ideal gas behavior. So if we do not have ideal gas, please remember this, for real gas will always behave like ideal gas at low pressure. Therefore, we can somehow use the relation of internal energy and enthalpy just now. So this equation, okay, can also be used for real gases under one condition, that the pressure is low, right? Okay, it says here the U and H data for number of gases has been tabulated. Actually, if you're referring to table 2 in your property table, number 2 is actually tabulates all the specific capacity for some type of other gases. Okay, and this table are obtained by choosing an arbitrary references point and performing some integration from this equation. Okay, so using this equation, scientists use this equation and do the tabulation, do the integration and get the value and tabulate the data in the property table. Alright, so if you can see, let me try show you. Right, so A4. So if you go to table A2, okay, this one A1, so this is A2. If you can see here, the ideal gas a specific heat of various common gases. For table A2A, is the specific heat capacity. You can see here there are CP and CV there, and also the gas specific gas constant for various common gases at temperature 300 Kelvin only. Alright, okay, and then table A2B is the specific heat capacity CP and CV at various temperatures. So this is the data tabulated between 250 Kelvin and 10,000 Kelvin only. Okay, for a variety of gas here, you can see air, carbon dioxide, carbon monoxide, hydrogen, nitrogen, and oxygen. On table A2C is actually another way of calculating the specific heat capacity using a function of temperature. Okay, so this is a much more complicated where you need to do some integration, but don't worry, we don't ask you to do it, to use this 2C table. Alright, so basically internal energy and enthalpy change when specific heat is considered constant at some average value. Okay, we can, in other words, it says that we can calculate specific heat capacity. We can calculate the change of internal energy using specific heat capacity, and also the enthalpy change specific capacity at temperature difference using the temperature difference by assuming it's linear. So we can do some what we call it, interpolation. Okay, interpolation by assuming the relation is in a straight line. Okay, so if we want to evaluate the CP value at certain temperature, which we don't know, we assuming just taking the CP value at higher lower boundary and higher boundary and interpolate as if it is a straight line. Okay. Alright, so there are three ways of calculating the change of internal energy and the change of enthalpy. Okay, the first one is using table, meaning if you do have the value in the table or value in the internal energy or enthalpy for gases, so you can use directly, you can take directly from that. Okay, for example, you have table A17. I'll show you. Table A17 is the property for some either gases. Sorry, A17. What is this? It's 16. Okay, so this is the A17. If you want to evaluate the internal energy change for air at various temperature, you can take this from the table the same way you read the internal energy of the water as pure substance. So you can just read off the value of the internal energy and also the enthalpy of air at various temperature. So this is A17 for air, okay, for air only, and then A18 for nitrogen. But this is in different unit. You just need to change into kilogram by using the molecular weight. Okay, so for table 18, the value of internal energy and enthalpy in different unit with the internal energy and enthalpy in table A17, but we can just change the unit using the molecular weight. Alright, so as I said here, there are three ways of calculating delta U and delta H. The first one is using table. Alright, the second one is by using the integrations from this equation. Okay, you need some relation between CV and T. So this is using this equation, but we don't really use this in for your syllabus. Okay, and then the second one is just the third one is just by taking, if you don't have just use this equation. Remember, delta U is almost equals to specific heat capacity at any temperature average and that temperature range, the times with the temperature difference. Okay, so so basically for you, we use this method and the third method, so we don't really use this method. Right. Okay, so this here is the how these two specific heat somehow related. Okay, so CP is actually equals to CV plus with the specific gas constant, right? So this is how these two value or property is related. Okay, this is coming from here. You can study by yourself, but the relation come out this way. Okay, CP, specific capacity for constant pressure, is always equals to specific capacity at constant volume added with some value, the gas specific gas constants. Remember, CP is always greater than CV. Right. Okay. And then the ratio between CP and CV will give you K value. K value is the specific heat ratio. So sometimes the question will give you K and CV. So they will ask you to calculate the CP by yourself. Right. Okay, now look at the examples given here. Alright, in this case, it says here the air is at 300 Kelvin and the pressure is kilopascal. Remember, once it says air, okay, we can assume air is actually ideal. Okay, ideal gas given at low pressure. Okay, so 200 kilopascal is considered low pressure. Okay, determine the changes in internal energy. Okay, you want the change of internal energy. So this is delta U per unit of mass, and per unit of mass meaning delta U lowercase, lowercase. Okay, and it's either we can use data from the table A17. For example, you can see here the system is constant pressure, and the temperature change from 300 to 600. So we use directly, okay, table A17, we go straight to 300 Kelvin. Table A17, okay, so go to 300 Kelvin, the value of U, internal energy, is here, 200, okay, 214 and 06, 214 and 06, and also 600 Kelvin. Where is it? Okay, 600 Kelvin is here. The U is 434.78 Kelvin. All right. So delta U equals to the change of U2 minus U1. Okay, give us 434.78 minus 21407. Okay, so much is that? 434 minus 220 degree. Sorry, 220. The unit will be in kilojoule per kilogram. Okay. Alright, the functional form, okay, we don't really use this because it requires some integration. The third method is average heat capacity. Alright, average capacity height value. Remember, average capacity, use this equation. Okay, delta U. Okay, delta U is CV delta T, right? C, constant volume. This is constant volume? Constant pressure. CP, okay, delta T. Right. Okay, before, sorry guys, wrong. Okay, so it asks for internal energy. You always remember that. Okay, internal energy, delta U is always related to CV, constant volume. Okay, CV delta T, and this CV is CV average. Okay, which is the temperature is between 300 and 600 Kelvin. Therefore, average temperature is 450 Kelvin. So we add 300 and 600, 900, and the average temperature is 400 Kelvin. Okay, so therefore we go to table A to B for air. The gas now air for A to B. Okay, to be here. Okay, so we go to air and we take the CV value of 450, that is 0.733. Okay, so this equals to 0.733 times the temperature difference is 300 Kelvin. Alright, So 300 times 0.733, so 219.9. Right. So wrong, no units. CV is 0.733 kilojoule per kilogram Kelvin times 300 Kelvin. Temperature difference, and give a 200.9 Kelvin kilojoule per kilogram. So this value almost similar. All right, using these two methods. Okay, that example 4.7. Okay, now example 4.8. Okay, this is where we use a specific heat to solve energy balance equation. Okay, example 8 here. It says that an insulated rigid tank initially contains 0.7 kilogram of helium. Okay, helium at 27 degree and 350 kilopascal pressure. A paddle wheel with a power rating of 0.015 kilowatt is somehow operated within the tank for 30 minutes. So determine the final temperatures. Alright. So if we look at this equation, we're strictly thinking about how to get the temperatures. Right? The temperature actually appears in CV. Appears in internal energy or enthalpy. Okay, internal energy or enthalpy. Okay, and this internal energy and enthalpy somehow a function of temperature, right? So we do the energy balance. So to be safe, we start with the energy balance. Okay, remember I want to use red color. Remember, energy change from the heat plus the energy interaction from the work somehow will change the energy of the system in terms of internal energy, potential energy, and kinetic energy. But the system doesn't say anything about kinetic or potential, so we assume potential energy 0 and kinetic energy is 0. Alright, so it gives us the heat interaction and work interaction will somehow change the internal energy of the system. Alright. Okay, since the system is insulated, okay, the system insulated meaning there is no heat interaction. Okay, so therefore this Q will be equals to 0. Okay, what is left with us is the work interaction will somehow change the internal energy. Remember, this is gas. Okay, gas system, helium. We can directly relate internal energy with the M. Okay, internal energy relate with the CV. Right, remember CV because the internal energy, right? And then the delta T, mCV delta T. And the CV here should be CV average. Okay, CV is CV average and at to 27 degrees Celsius or 300 Kelvin. Okay. So you just take initial values, okay. Okay, so it says here a paddle wheel with a power ratings this much and this much. So this give us idea that it is what is this? Shaft work, okay, shaft work for 15 minutes. So we need to evaluate the amount of shaft work in this case. So the work interaction in this case is actually shaft works into the system. And always positive because it is in. And then give you mCV delta T. So we need to find the temperature, final temperature. So shaft work is calculated from the power times with the time. Work is power times time, right? Okay, so 0.015 kilowatt, or actually you can write kilowatt in terms of kilojoule per second times 30 minutes is 1000 seconds, right? Okay, so it gives us what? 0.015 times 1500 is 20 kilojoule. So 20 kilojoule is the amount of work interaction in terms of shaft works to the system. All right. So so we have 27 kilojoule from the work interaction. Will change 0. kilogram of helium. Okay, using specific heat capacity of helium. So we can find the specific heat capacity of helium from table 2B. So we have, helium, 2C. 3, where is this? Okay, 2A. Alright, so table 2A, we have helium in this case, so we need the CV value because we are calculating internal energy. Okay, so we take 3.1156. 3.1156. Okay, times 3.1156 kilojoule per kilogram Kelvin times delta T. Okay, so it gives us kilojoule, kilogram. So give us 14.38 Kelvin delta T. Okay, since the initial temperature is 27 degrees Celsius, so T2 is T1 plus 12.38 degrees Celsius or Kelvin, because the difference in degrees Celsius is the same difference in Kelvin, right? Okay, so 27 is 39.4 degrees Celsius. Okay, or the words 312 Kelvin. Oh, I use Kelvin then. T2 is T1 plus 12.838 Kelvin. Give us 312 and 38 Kelvin. Final answers. Okay, how about the final pressure? Okay, remember this is considered ideal gas, right? Okay, where's this? Helium. Okay, helium is considered ideal gas. Alright, so we can directly use ideal gas equation. Relation P1 V1 T1 equals to P2 V2 T2. Okay, why we can, okay, the volume is constant, both V1 is always V2 because it is a rigid system. Okay, so we need to evaluate P2. P2 is P1 times T2 over T1. So we have 350 kilopascal times T2 is 312.38 over 300 Kelvin. Okay, so give us 351. 351 kilopascal. Okay. Alright, I think I'll stop here. We stop here how to use the specific capacity in solving the energy balance. Okay, I will show you, I'll stop this video because it's quite long now. Okay, and later I'll show you the example for 10. Okay, thank you so much.